Welcome to today's SCA webinar with Dr. Fermin Fernandez Ibanez of Subsurface Alliance. He'll be speaking on excess permeability in carbonate reservoirs, curse or blessing. Before we start today's webinar, I'd like to ask a few questions about the demographics of the audience. So let me start the polling questions. And our first poll is, what is your primary discipline? So we're starting to get responses now. Quite a few geoscientists in the audience, a few petroleum engineers. Answers are still coming in. So most of you have voted now. So the majority are geoscientists, 79%, 16% petroleum engineers, and 5% petrophysics. So the next question is, how many years of full-time experience do you have in the upstream oil and gas industry? So we're starting to get some responses now, quite a spread. Most of you have voted, so I'll share the results. It looks like most of you, 36%, are in the 11 to 20 year range, but we also have 20%, 18% over 30 years, and 32% at 21 to 30 years, and 14% at the 1 to 10 year range. So we have a couple more polling questions. Let's launch this next one. What is your experience with excess permeability, such as fractured or karst reservoirs? And your answer can be either blessing or curse. So if you've had karst experience, is it a blessing or a curse? Starting to get answers. It looks like it's roughly half and half. That's interesting. So most of you have voted now, and it looks like about 58% call excess permeability a blessing and 42% call it a curse. So our next question is, how often do you look at core, the actual rock, in your job? So it looks like several of you look at it frequently, and some of you are occasionally. All right, good. Most of you have voted now. So our results, 52% occasionally look at core, 24% frequently, 16% almost every time. And then we have one more question. How often do you use image log interpretations in your job? So same type of responses. This is, how often do you use image log interpretation? Okay, most of you have voted. So the results are 42% frequently, 29% almost never. And then the rest of the distribution is spread between almost every time and occasionally. So thanks for sharing your thoughts on our polling questions today. And let me share my slides here. So this is today's webinar on excess permeability in carbonate reservoirs, curse or blessing. And Dr. Fermin Fernandez Ibanez is our speaker. And he is the managing partner at Subsurface Alliance. He's a geoscientist with more than 15 years of experience. And he has been working in this field for some time. He started with a degree from Granada University in Spain, a PhD, and worked for Geomechanics International, GMI, before joining ExxonMobil. He became a corporate subject matter expert for fractured reservoirs. Fermin also has experience in geothermal and carbon capture and storage projects. He's worked in many countries around the world. He's very well published, and I'm sure has a lot of more information to share on this topic. So just a little bit about subsurface alliance, and this shows you the interactions between matrices, fractures, and karst, and where is the sweet spot in the middle of all of those. I'm sure Furman's going to go into more detail on this topic. Subsurface Alliance is a group of network of subsurface specialists, and they are involved in a number of different topics listed here. Some geoscience, some geomechanical, some petrophysical, some reservoir engineering, but lots of interesting topics in which they have technical expertise. SCA is offering some live online classes that are coming up in 2023. We have Bob Barbet speaking on the topic of best practices for new well fracs and legacy well refracs. That's 8 hours spread over several days in half-day increments, and it's offered virtually. And then in February, we have Dr. Larry Lake and Dr. Jerry Jensen speaking on managing mature oil fields with CRM, capacitance resistance modeling. Again, it's half days spread over several days virtually in February. And Dr. John Lee has a couple of courses that he's offering live online through SCA. We have production forecasting for low perm reservoirs and PRMS and SEC reserves and resource regulations, 2 separate classes, one at the end of February and one at the end of March, again in half-day segments offered over several days. This is a busy month for webinars for SCA. These free webinars are offered to our clients around the world. PK Pandy will be speaking on navigating CCUS, the landscape, historical context, opportunities, and participation. And then we have Bill Ott and Jim Smolin, and they'll be speaking on cement evaluation and remediation. And of course, SCA offers training courses that come to your location if you would like to have an in-house course, and we also have public courses available. In addition to training, we also offer consulting, direct hire services, projects and studies, and other consulting services. So I'm going to give the presentation rights to Furman, and it's all yours.
All right. Thank you, Susan. Happy New Year to everyone. Someone told me this morning that it was okay to say Happy New Year until January 15th, so I think we're good. Let me know if you can see my screen.
Yes, looks good.
All right. Now let me see if I can get my pointer ready. All right. Excellent. Well, so I want to start the presentation today with a couple of definitions of terms that I'm going to be using throughout the presentation. And to help me with that, those definitions, I'm going to be using that figure that Susan showed earlier. On the left is a ternary diagram where you can see on one corner your matrix, and then that matrix through mechanical failure can lead into the formation of fractures, but also that same matrix through dissolution can lead to the formation of karst or bugs. The same fractures can later see fluids running through them that leads to dissolution, and you can end up also in this lower corner of the karst. So the idea is that fractures and karst is almost like a continuum, and all that portion of the pore space and the pore system is what I'm gonna refer to as non-matrix, because you want to treat them often together, right? So you don't want to work fractures and then karst, but try to work that as a whole. And that term non-matrix is really borrowed from the engineering world, because when you have these type of features, you want to model them and simulate them. Typically, you need a dual porosity, dual permeability model. These are basically 2 collocated grids. In one, you have the matrix properties, and in the other one is where you're going to put your non-matrix properties. That would be both karst, fractures, and anything that you can have in between. The presence of non-matrix in carbonate reservoirs is typically associated with the phenomenon of excess permeability. And just to put it simply, this excess permeability refers to the difference between the permeability that you can measure in core plugs from wells. So these are two wells, and these are permeabilities from core plugs, and the permeability that you would measure from a well test. Typically, that well test permeability is greater than the excess than the permeability from the core plugs, and that difference is what we refer to as excess permeability. Why is this? Well, usually there is a sampling bias. When you are taking core plugs, you are not able to usually get a plug if you have an open fracture or if you have a bug, right? So you don't really sample those features. The other issue is the scale. Some of these features are much larger than your core, and therefore they are typically not sampled. When you run a well test, then the well test investigates a much larger area, and therefore is when you see the contribution to the permeability of the Nonmetrix. So now I want to introduce two helpers that I have here today. One is Dona Maria, right in here, and also Bob the Bee. Watch out for Bob the Bee, because he is going to be just pointing out to some takeaways as we go through the presentation. So actually, Dona Maria, she owns a hydrocarbon, an oil and gas company, and she has some reservoirs. She likes carbonates, like I do. And she has a very different experience with excess permeability. She sometimes thinks that's a blessing, just because wells that are drilling to or are tapping into Nonmetrix, they typically have great PIs, greater than 50 barrels per day per PSI. They deliver excellent rates, more than 30 kbds. Great reservoir connectivity, and also that means the presence of Nonmetrix often brings additional in-place volumes. But sometimes things can get complicated, right? And that's where she thinks, well, man, that's a curse, because they have issues, well-controlled issues. Sometimes you cannot drill to TD. In EOR operations, they often have poor sweep efficiency. They see early breakthrough of injected fluids, and end up with having a lot of issues with water conformance. And Dona Maria is now getting interested, like everybody else, in carbon capture. So she wants to also put some CO2 in some carbonate reservoirs. And kind of the situation is very similar. A carbonate reservoir, from a carbon capture perspective, can deliver or have very good injectivity and high storage efficiency. At the same time, it's going to have a lot more uncertainty on the shape of the plume, and also she thinks it can compromise the containment. The one thing that Dona Maria has learned, and I have also learned this throughout the years, is that really the key issue here is to be able to recognize the presence of Nonmetrix in your reservoir. And when you fail to recognize these early on, is when you when you end up with suboptimal development plans that can affect your facilities, your well count, your well placement, and your design. So what I want to do today here is kind of walk you through a number of examples, observations, workflows, techniques that we have developed throughout the years that try to identify the presence of Nonmetrix, and then put that in a geologic framework that can be used for building a model, and then try to add a little bit more information to these Nonmetrix features from the dynamic perspective. What is the permeability? And how that can impact your reservoir performance. So first, I want to start just with a tool that I like to call the VVR Plot, and it's used from a screening perspective. And what it uses is just drilling data, drilling reports. This VVR Plot basically is an empirical plot where we have about 100 discrete loss circulation zones. And what we found is that depending on what is the feature that is driving that loss circulation zone, the signature in this plot might be different. And you end up with these different regions and type losses that are indicative of the feature that is driving or responsible for the losses. Perhaps the most important threshold here is the 50 cubic meters per hour. When the rates of the loss circulation zone are greater than that, it usually means that you have a cave or some karst type feature. when the rates are lower than 50, are usually associated to natural fractures or touching plugs. And of course, the closer you get to the origin, the features responsible for the losses are much smaller, and you don't really have the resolution to differentiate between one feature or the other. As an example, I have a type 4 loss circulation zone and a type 2 here. And what you actually see when you run an image log. Type 4 is a cave. It's about 2-meter tall cave, and you can see the lower part of the cave has some sort of fill. Here you have a few open natural fractures that are the ones that drove the losses with a rate that is lower than 50 cubic meters per hour. So how do you use these? Well, I like to use that as a screening tool. As I said, this is an example where, first thing I do, if I have, a fair amount of wells, I go through the drilling reports, I try to collect the information on loss circulation zones, and I plot them in here. So this is an example from the Brazil result, about 30 wells. And what you see is that most of the losses are plotting in this area below the 50 cubic meter per hour. What that is telling me is that most of the features, non-matrix features, are likely to be fractures and perhaps some touching bugs. And I have, the occasional feature that might be a cave or a karst, as opposed to this other example. This is a Miocene carbonate buildup in Southeast Asia, and you can see that there is a large amount of the losses that are actually sitting in here, suggesting that this particular reservoir has a large proportion of caves or of karst. So when I look at these two, my mind goes to two different ideas. The first one, I'm concerned about reservoir connectivity, sweep efficiency, while this one, lead me to think about in-place volumes, reservoir energy. So it is a good way of getting started and kind of quickly do a bit of a screening of what you might have in your reservoir. And this is really good when you have all wells where there are no image logs, there are no core, the losses, the drilling information, it can actually add a lot to your reservoir characterization. The next piece here is really the core. You want to look at the core. You want to make an observation on what type of non-matrix features you have in the core. And these are some examples of where you might find when you look at the core in a reservoir that has no matrix. These are examples all from the results in Brazil. You can have fractures that are being dissolved out. You can see how the walls are not matching anymore. You can have centimeter scale bugs like this one in here, where you can actually stick your finger in there. You can have fractures that are just bed bounded, like these ones in here, confined to certain layers that are more prone to fracturing. Some interesting fractures like this one that are relatively short, but they show pretty wide aperture. So that has a higher potential for contributing to flow. And then you can see things like these millimeter scale bugs that actually gives you a very pervasive, well-connected network of pores that actually have fairly high permeability values. When you run, for instance, a PLT, you can see that there is a lot of contribution coming from these type of features. But you don't want to stop there. You want to go one step beyond. Just don't say, well, yeah, I saw fractures, I saw karst, I saw some bugs. Now, try to look at the features with a process-based approach. Make observations on the features that tell you something about what is the process behind that feature that you see. And that will give you a much better capability when it comes to developing predictive models. So the example here is with fractures. On the left, I have a couple of fractures that are filled with clay, filled with carbonate debris, or carbonate micrite. That means that these fractures are likely open or connected to the subsurface, to the surface. So the interpretation is that these fractures are syndepositional fractures. They form early on. Syndepositional fractures tend to form mostly around the margin of the platform. So if you were to populate a model, that's where you would tend to put most of your syndepositional fractures, around the margin, but perhaps not in the platform interior. On the right-hand side, you can see examples of fractures that are interpreted as burial fractures. They are fractures, a lot more dense network of fractures. They are opening mode fractures, often associated with stalolites filled with clear calcite crystals, and they sometimes show evidence of lake corrosion or bitumen. So all of that indications that they form in the burial realm. And they might actually occur in different places than disinterpositional fractures. And the controls on these burial fractures might be related to more mechanical stratigraphy instead of the position in the platform. So again, if you can make these observations, you're in a much better position in terms of, well, not all the fractures are created the same, right? So I'm not going to model them the same or together. The next piece of information that is great, and it's probably the best data set after the core, are image logs, because they provide a lot of coverage in your wellbore. And you can see features just like the ones that I was describing before. You can see caves, like this one in here is about 1 meter tall, open cave, some sinusoidal features interpreted as fractures. Perhaps that curvy edge can be interpreted as a enhanced fracture by dissolution. These are examples of fractures coexisting with bugs in silicified intervals that are brittle and more prone to fracturing. And these are examples of those millimeter scale touching bugs that might not seem much on the image logs, but when you run PLTs, you can actually see that that's where most of the flow is coming from. Nonetheless, all these image logs are remote sensing techniques. So that is not the ground truth. And that's why it's super important, in my opinion, to integrate core with image log. It is a tedious process, but actually worthwhile doing it. So the process here is easy. It just takes time. You look at you have your image logs, you have an interpretation of your image log. You can do it yourself, or you can use a third-party interpretation, and then you want to put that in depth with your core. The idea is to look for features that you can see both in core and on the image log, like this stylolite, like this clay layer, or like these changing facies, right? And you can make that type. With that core to log shift that is fairly precise, down to a few centimeters, now you can start validating your image log interpretation. And you can go sinusoid by sinusoid and look for that feature on the core and say, well, yeah, I can see the fracture here in the core, so I'm going to accept it. Or I don't see anything, that is a misinterpretation, so I'm going to reject that interpretation. This is an example of a test that we ran in 13 wells. Most of these interpretations were done by third parties, different companies, different people throughout the years. What we found is that about more than 50% of the interpretations were rejected. We couldn't find a fracture on the core. So at the end of the day, what you are doing is over-interpreting, and you are suggesting that you have a fracture density that is much higher than what you actually have. As an example of what is the impact on building models, let's take a look at these two plots, stereo plots in the lower part. Here is an unfiltered, so before doing that core to log, you can see all the fractures that were interpreted on the image logs. So you can see a dominant east-west direction trend of fractures, but then you can see that there is a lot of other fractures in different directions that can provide connectivity throughout the reservoir, and perhaps not impose a strong permeability anisotropy. After you do the calibration and you reject a lot of those interpretations because they were just misinterpretations, you end up with a strong preferred orientation of your fracture, one dominant set that is going to impose, again, a very strong permeability in your reservoir. So very, very different. Perhaps don't have as much connectivity. So this first model is going to give you a tank-like reservoir. The second one is going to have anisotropy in the permeability. Other thing that we learned, as you look at the image log and you look at the core, there is so much that you are learning because you're looking at the rock and your image log. Simple things like these continuity rules. If you see a sinusoid that is totally continuous and you interpret that as a fracture, the chances that that is a fracture is pretty high. The less you see of the sinusoid, the more likely you are misinterpreting that feature. So there is a correlation between continuity and chances that you are gonna be rejecting that feature when you do the integration with the core. And you can take it even one step further. Now that you've done all that work on the image log and the core over the interval where those two overlap, you can make observations on, in the case of these interpositional Maria fractures, you can see that interpositional fractures have some characteristics that are different from the burial fractures, and you can use that to interpret your fractures away from where you have core control. So you can make an informed interpretation of sinusoidal features away from core control and assign a genetic type that is going to be tied to a process that later you're going to use for developing geologic concepts. So far, I've talked about a lot of information that is more wellbore centric. You can see fractures in the core, fractures on the image logs, but this is a multi-scale problem that can extend to much larger or greater scales, to the point that you can actually see some of these in seismic. And this is an example of a pattern that is a maze pattern, and these high amplitude events can be interpreted as dissolution enhanced fractures with two perpendicular sets, just like what you see in modern caves. This is an example of the Wing Cave in South Dakota. In other cases, these caves are not developed through or don't have a structural imprint. They are more like isolated chambers, like blobs, and that's how they look like in seismic. You can see in here, in this example from a carbonate buildup, some high amplitude, low impedance events or mega amplitudes that by drilling them have been proved to be open caves. These caves actually follow that blue line that is the outer slope to, the outer platform to slope transition, and they are associated or they are interpreted as freshwater caves that form when this buildup was an island, so way before everything was buried. So let's just talk a little bit about these caves. This is how they look in present day in analogs, just more like a pancake type of feature, a few meters tall, limited lateral extent. And when you drill shallow wells in some of these carbonate islands, you see similar features to what we see in deep reservoirs today. These are examples of those caves at 10 or 11 meters. That's another cave in here. And that is not too dissimilar to the feature that I was showing early on in here, or this one. It's a 2 meter tall cave, open cave in a carbonate reservoir that is sitting at 4,000 meters depth. So they form near the surface, they get buried, and actually they can stay open and be preserved till today. So someone told me once, it's like, well, you know, we drill a well, we just happen to drill through a cave. So what is the meaning of that? Well, the chances that you're gonna drill through a cave are pretty slim. So the fact that you drilled the cave means that there are likely a lot more around. So what we did is run this Monte Carlo simulation, where in a volume of rock that we thought it was likely, to have some karst, how many caves we can stochastically place in that volume, with the only condition is that my well has to intersect only one. And this is one of those realizations. What we found is that you can have between 650 and 750 more caves in that volume. And that has significant implication from a pore volume perspective, because depending on what is the matrix porosity, that can imply a pore volume uplift between 2 and 20%. So if you have a cave in your image logs, you may want to consider what that means from a pore volume perspective in your reservoir. The end goal of all this is really to put together a conceptual model. Some colorful picture like the one that I'm showing in here, where based on your observations in the core and the image logs, and help with your drilling information, you try to tie that to concept and decide areas where you are more likely to find different type of non-matrix features. For instance, here is again the example of this carbonate buildup. The blue line again represents basically the coastline, the outer platform to slope transition. You can see that that is an area where you have increased probability of having seen depositional fractures, increased probability of having caves, while your burial fractures can coexist with them, but also they can be in the lower part of the slope or in the platform interior. Right? The information collected through all that observation and measuring in the core, that is basically translated into a model that could be something like what I'm showing here. That's a DFM model. But up until now, everything we've done is mostly static. So the question still remains: what is the dynamic potential of these features? Are they all connected? Are they all effective to flow? So the second part of this presentation is going to be geared toward trying to answer some of these, or at least put a little bit of a constraint to those questions. So let me go back again to the image logs. Well, here I want to just talk about perhaps a myth. People look at image logs, they find a fracture that is conductive, and they say, well, if it is a resistivity tool, they say, well, conductive, that means that it's filled with mud, so it must be open. And that might be true. That is the case of this example in the far left. Fracture that is conductive, and when they drill through that fracture, they lost more than 150 cubic meters. So it's a fracture that is conductive, that is open, and perhaps most likely is effective to flow. The next case is a fracture, or a couple of few fractures that are resistive. So if they are resistive, they are likely filled with something. So most likely they are not going to contribute to flow. They are filled, they're not open. Well, and that's fair enough. We don't have a lot of information here to disprove that. It kind of makes sense in that sense. The next case is just like the first one. It's a conductive feature. Actually, 3 sinusoid, 3 fractures that are conductive. So you could say, well, the well took no losses, but maybe they are not that big. They are not that well connected. So they should be open fractures because they are conductive. Well, when you do the integration with the core, you see that these fractures are filled with clay. The clay is also conductive. So now you are misinterpreting the dynamic potential of this feature. So remember, the resistivity character of fractures in image log is no guarantee for the dynamic potential. The integration with core is super useful to at least flag some of the reservoir where you might be in this case, and you need to be careful with that interpretation of conductive means open. Let's take a look now at the dynamic signature of the caves. Not very different from what you see with fractures. We're going back to that cave that I was showing early on. Tall cave, about 2-3 meters tall, with perhaps a crackled breccia or some sort of collapsed roof where you can see fractures, losses while drilling. So there is a loss circulation zone in there. They ran a PLT and they saw nothing. There was no flow coming from that cave. Here is the temperature log that went with the PLT, and you see that it's pretty much flat. So 2 interpretations here. One is just a cave chamber with limited lateral extent, no well connected, and therefore it's just not flowing. The other interpretation is that, well, let's go back to your drilling report and see what happened. How did they manage the losses? Did they use a lot of LCM, loss circulation material, or cement? And if they did, maybe that is what is preventing this feature to flow afterwards. So well-controlled operations can actually mask the dynamic signature of caves in particular. On the right-hand side, there is an example of what we interpret as 2 or perhaps 3 stacked caves. In this case, the caves are not conductive. They're actually resistive. And that's because the mud that they were using while drilling this well was an oil-based mud. When they run a PLT, you can see the cumulative production rate kicks in as the tool is passing by these caves. The temperature log also shows some anomalies suggesting that there is flow coming from this feature. That's great. but there are some considerations that have to you should take when you have these type of features. Features that dominate the flow. Basically, what can do is mask the contribution of other features, because there is just so much that you can flow through the well, and this feature is just delivering everything. Other features that might be effective don't have the ability. There is no room for them to contribute. So you will see all the fluid coming from this feature. Now, over time, maybe this feature is not well connected. Maybe this feature is drained out. Maybe as you are depleting your reservoir, the compressibility of the non-matrix is changing and you are closing certain paths. So you can see through time how that flow profile of a well can change, and features that were contributing, even dominating the flow early on, 10 years later or 5 years later, they are not producing anymore, and now the flow is coming from some other features. So important to keep this in mind, and that's the value of having multiple PLTs in a well through time. Together with the PLT, there is often a well test that is done. So here is an example of a well test, and this is a pressure derivative that goes with it. In the early time of the well test, you can see that the derivative is stabilized. So here we can get an estimate of what is the permeability thickness, about 17,700 millidarcy meter. And the question now is, well, that is the permeability thickness. How do I distribute that in the well test interval? It's about 100 meter well test that I've been having here. One option is you say, well, it's 100 meters and that's my permeability, so permeability thickness, so I'm just gonna distribute them equally. And I get an average permeability of 177 millidarcies. But someone could say, well, hang on, I have some image logs. And I have looked at the image logs and there is no matrix. It seems that there are some fracture, there are some bugs. And I think maybe these features, because of the drilling experience or my observations in core, maybe those are the ones that are driving flow. Therefore, my effective thickness now is the non-matrix thickness. And if I use that non-matrix thickness, all of a sudden, the average permeability goes up to 650 millidarcy. Then you decide to run a PLT, and the PLT shows that the flow only comes from an even shorter interval, 23 meters. Now you can distribute that permeability thickness in the 23 meters and you get a much higher average permeability. But with the PLT, you can actually see the relative contribution of the different intervals. That relative contribution of the intervals allows you to allocate permeability. And you can see that then there are some intervals, like the second and the fourth interval, where the permeabilities are in the order of Darcy. Now, you can get, this is a much different perspective view of your reservoir permeability architecture than the first one, where everything was on average 177. So fairly homogeneous versus a very heterogeneous reservoir from a permeability perspective. So PLTs are super useful to understand flow partitioning at the wellbore, and it's really a first step toward understanding reservoir heterogeneity from the permeability perspective. So now we're getting into the last part of the presentation, and what I want to do is take a bit of a case study, a well where we can make some observations, where we can derive some concepts, and where we can integrate that with well tests and talk about maybe what are some realistic values of permeability for these non-matrix features. So this is well A. So on the left, you can see for well A, we have a caliper log. You can see the lower half of the well is fairly enlarged. There is an image log. This is an acoustic image log. And you can tell just from the way it looks, the lower part, there's something different going on there than the upper part. They collected core, and they had to stop the coring operations because they started having losses. So they couldn't core anymore. They continued drilling with losses all the way down to TD. And there is an interpretation here of the image logs that is validated with the core over the interval where these two overlap. The observations are, there are different type of features, millimeter scale bugs, there are centimeter scale bugs, there are fractures, bed bounded fractures. And the other piece of information that I have here is a mineralogy log. And you can see how the area of yellow it gets greater in the lower half of the well, and that's where you have an increase in the silica. The lower part of this well is silicified. So observations that were made on the core and on the image logs in the upper part. Millimeter scale bugs, both in core and in the image logs, but also fractures that seem to be confined to some of these silica layers. Those are very different from the observations made in the lower part of the lower half of the well. That very beginning of the lower part of the well, we still had some core. The core was very fragmented. A lot of difficulty putting pieces together, but you could make some observations like some of these bugs that are almost the size of my fist. And there are some fractures that show dissolution enhancement. That is consistent with what the image logs are showing deeper in that same section. Large bugs and also sinusoidal features that suggest the presence of natural fractures in a silicified portion of the wellbore. So that increase the brittleness of the rock. The rock is more prone to develop fractures, but also the silicification process can lead to creating additional porosity. If we take a step back here and we look at a bit of a big picture, looking at the seismic, what we see is that the well is located in a structural high, and the lower half of the well seems to be intersecting what was interpreted as a fault. So perhaps what we are looking at in this lower part of the well is the expression of a damage zone. So just from the, if you will, static observations that we've made in core and in the image logs, the upper part and the lower part are very different. I would expect that the well test in the lower half versus the well test in the upper part of the well would be different as well. And indeed they are. Here are the pressure transient analysis for test number 1 and test number 2. Very different trends. This is what we term the upward trending type of derivative, where you can see that in the early time, there is some stabilization of the derivative where you can derive your permeability thickness. That's a fairly high number, about 100,000 millidarcy meter for about 50 meter thick interval. And as you move away from the wellbore, so that's in the late time, you can see that there is an uptick in the derivative, suggesting that away from the wellbore, there is a decrease in the transmissivity, right? So whatever is driving that high permeability seems to be fading away as you move away from the well. That's a very different story from what you see in well test number 2. Massive drop in the pressure derivative, a lot of skin, and no stabilization at all in the derivative. You can see that the pressure derivative just continues to go down almost to the 8 or 9 hours and then start recovering. This is what we call a sharp rollover type derivative. And what that suggests is that the well is intersecting a massive non-matrix feature that extends ways from the wellbore. And that is where you are investigating and continue to investigate for the first 8 or 9 hours until it seems that now you start seeing more of the matrix. And that's where you start seeing a recovery of the derivative. Permeability thickness in this area is about 500,000 millidarcy meter. So for 30 meters, we're talking about 17 darcies. That's average permeability. So with this at hand, the next thing we can do is start putting together some geologic concept. We can wear our geologic or geology hat and then start drawing some sketches, some cartoons. You can do that in your whiteboard. So for the first case, test number 1, what you can see is that we made observations on, we have these layers of fractures that seem layers that are fractures that have bed under fractures, but also we have these touching bugs that are also organizing layers. So perhaps what we have here is just these hypermeability layers that are the ones that are driving this hypermeability that we observe at the well test. But as you move away from the wellbore, these layers have a limited lateral extent. So they go away, and the result is that decrease in the transmissivity as you move away, because you are losing now permeability thickness because those layers are not there anymore. As opposed to the case of test 2, where based on the observations, we are likely investigating with the well test a fault zone. And the fault zone is dominating the flow, dominating the pressure derivative. And what you are seeing here is just the expression of that fault, and the well test just that continues to investigate the lateral extent of this major fault. So with these concepts, you can start now putting that into a geologic model, and then you can get into that iteration between you and the reservoir engineer, where the model goes back and forward because they don't get a match or because things they just don't seem right. So there is often a lot of time that goes into those iterations. Now, there is one step that you can take before doing that that can actually alleviate that and can reduce that cycle time to a minimum. And that is just a validation of your concept using numerical models. And that's where you get together with your friendly reservoir engineer and your friendly well tester. Either you can get lucky and you have a really good well tester that can show you how to use some of their software, and you can start running some of these numerical models. You can just sketch in some of the commercial software that is out there your concept. This is the concept of these mounds with hypermeability layers. So in a cross section, I have layers like these that have limited lateral extent that I assign 2 Darcy to each of them, and then a background matrix of 100 millidarcy. On a map view, that is the extent of the different excess permeability region. Then you put your well, and then you can run your you can do your forward modeling, and sure enough, you get this sustained upward trend signature or shape, just like the one that we were seeing in the actual data. So with that at hand, you can at least have some confidence that this concept is validated, is at least one plausible explanation for the permeability architecture in the reservoir near the wellbore. So if you are interested in this, I really encourage you to take a look at this paper that we just published. It's an excellent work by Jordan Mimon. He's well, I learned a lot from him, and he's one of the best well testers out there. So I really encourage you to take a look at that. It has a lot of good insight for geoscientists as well. My last slide here, I want to dedicate that to well test again. I learned so much, and I realized how much information is in there that often it gets ignored or just not maximized, that I think is worth having a bit of a discussion as a closing slide in here. So this is a simple case where I have a well, and this is a fault zone. It looks like a slide, but it's actually a fault zone. That's what I'm trying to represent in here. And the idea is that the fault zone intersects the wellbore at some location. And now I have the opportunity to do a DST, well test. And the question is, what is the interval that I should test? Well, that depends on what is your well test objective, right? What do you want to get out of that? And that will basically depend on whether you are in an exploration phase or a development phase or in appraisal phase. So if you want to select the lower part where the wellbore intersect the fault, where you are going to have a lot of Nonmetrix, just like what we saw before, most likely your pressure derivative is just going to look like this. It's going to be noisy. very noisy. You're not going to be able to get any quantitative information out of the well test, but your PI, your well productivity index, is going to be through the roof. So from a exploration well perspective, that's great. You show that those wells have a lot of deliverability. Now, if you are in a appraisal situation and you are trying to de-risk your prospect, and your question is, well, what is the permeability of all these faults that I have in my reservoir? Should I worry about them? Are they even conductive or not? Well, then you can come up a little bit higher, and you can select an interval like that where you are close to the fault, but you are not intersecting the fault zone, so you avoid all the noise, but the signature is going to be dominated by the fault zone. And basically your well test is going to fully investigate and provide quantitative information about the known matrix that is making the fault zone. The other case is that, well, I still have some uncertainty in the matrix, and that's kind of my main concern, but I would like to know something about the faults as well. So you can select an interval like this, where you are farther away from the fault, and your early time is going to give you information about the matrix permeability, but then in the late time, you're going to get, at least you're going to get to detect the known matrix and say something about whether that is permeable, like what you're seeing here, or if you have more of an uptake tendency that will tell you that that fault might be a baffle or a seal. So very, very, very useful discussion to have, so you can maximize the value of information that you get in well tests, which are not cheap. So just to wrap things up, I have here a bit of a few takeaways. You can see Dona Maria is right there already taking notes, so I encourage you to do the same. And some of the things that I want you to walk away with is, use all the information that you have at hand. The word here is integrate. Integrate, integrate, and integrate. And integrate from the drilling data all the way to the well testing data that you have. But don't forget the core, because at the end of the day, that is your ground truth. Use a genetic-based approach when you are characterizing the known matrix, trying to understand what are the processes driving the different type of known matrix, and that will put you in a better position to distribute them in a conceptual model. And remember this, not all fractures are formed the same, so please don't model them together, like just throw them in the same bag. And that goes, the same applies to karst. Do not underestimate the presence of caves. They might actually provide additional pore volume and energy to the system, so that's something to look into. And do not believe everything you see on image logs. You want to take that and convert that to the core when you have it, and do that integration and learn basically from your mistakes. You make an interpretation, and then you validate your interpretation, and you learn from what you did wrong, and that's okay. Use PLTs as much as you can to try and understand the heterogeneity in the permeability architecture. And if you don't have them, you can get creative. Look at the drilling reports, or perhaps use the image logs together with some of the wireline logs, and do a ranking of dynamic potential. Go beyond the static characterization. Maximize your well test, and then once you have concepts put together, try to test them using these simple numerical models, like the ones that I was showing before. One commercial software here, the one that we use, Sapphire. Of course, if you have an opportunity, have a say in the well test design, and make sure that you maximize the value of information. Make sure that when you run the test, you get the information you need to de-risk your prospect, depending whether you are in exploration phase, appraisal, or development. One last slide with references. A lot of those is just the sources for the images that I used today, but I want you to pay attention to this second part. That's more like recommended reading. Those are papers that if you are interested, I found them very useful. Some of them are along the lines of what I presented here today. Some others have a very completely different perspective, and I encourage you to read them as well, get different perspectives, and kind of come up with your own point of view. And with that, just want to say thank you. Dona Maria also say thank you to everyone for attending the webinar today, and I want to thank SCA for the opportunity to present. Cheers.
Thank you, Fermin. I'd like to remind the audience that you're muted, but you can use the GoToWebinar question feature to pose your questions. And we do have some questions. So it seems, based on the survey results, we find it difficult to obtain good quality cores in naturally fractured reservoirs. We seem to require the poorest quality rock and little of the highest quality or zones that provide the high permeability. So the challenge of acquiring core in the karst, or the highest permeability. So what is your experience in how to get the best coring results as you're designing your core?
Well, I think that is just a fact that we have to live with. Where you have these big features, if you have a cave, there's no way you're going to core a cave. And if you have large open fractures, you're going to core that, and you're going to end up with rubble or issues that are not going to let you actually see those features. So the open features, I don't think there is a good way of getting around that. Now, in fractured reservoirs or karst reservoir, there are other features that are smaller that you get to core. And I think that's where you can get the value of trying to make observations. Like the examples that I was showing before, those syndepositional fractures, they were filled with debris. And that's why we were able to core them. They're not the ones that are flowing. The ones that are flowing, we couldn't core. You can see them on image logs. So that's when you bring image logs, but you won't be able to core them. Now the value is on the observation that we made on the material filling the fractures. They are filled with early marine cements, or they are filled with carbonate debris. And that suggests that those fractures were syndepositional. And those fractures, therefore, tend to form in the margin. So now I know that I have probably a lot of syndepositional fractures forming in the margin. And when they get big enough, they are often open, and those are the ones driving the flow. So it's not so much trying to core the interval that is almost impossible to core, but actually get information from those pieces where you can core. And remember, this is a multi-scale problem, so you can make observations in the small features, and then you can extrapolate that to the larger ones.
So I was interested in the frequency of the data that you collect in a surveillance plan. How often would you collect the PLTs and pressure transient analysis tests in a typical situation?
Well, I guess the response to that is how much money do you have, right? But because these are really expensive, right? So I've seen, in my experience, cases where there is no money, so there is no even PLTs that are collected. That's where you need to get creative. But there are other cases where, after 20 years of production, you can see that they do this in every 5 years, maybe every 8 years, and they go and do a PLT with a well test. In other reservoirs, they only do a PLT, and that can be done even more frequently. I've seen that done every year. And maybe you don't do it in every well. You select, a few wells one year. The next year you alternate the wells. So I think the frequency question, I think, space every 4 or 5 years. In my the sense that I get is that that's probably a good spacing. But again, that's all limited by budget.
And are there any challenges in integrating PLTs and pressure transient analysis tests that have been taken 20 years ago as compared to current day technology?
That's a really good question. I think yes, there will be a lot of challenges with old data. New technologies have really good gauges where you can actually go down to just crazy resolutions. From 1 psi, you can actually put together a history of pressure connectivity. While for all data where the gauges have less resolution, I think you're going to be challenged in that sense. So I think It's just all data is not that you're gonna discard, but you're not gonna be able to get as much as you can get today from the technology using gauges with the ones that have a crystal of quartz, for instance.
Of course. Well, it looks like we're at the top of the hour, so I want to thank our audience for attending today's webinar. Later today, you'll receive a link to the recording of the webinar. You'll get an evaluation form and a link to SCA's website with more information about the services provided by Subsurface Alliance, including those related to carbonate reservoirs. Thanks for joining today. Goodbye.
Thank you. Goodbye.